So, our conical pendulum. There's the cone that it was moving around in. Bob, our helicopter called Bob, is moving in angular velocity in a horizontal circle. Let's just throw some dimensions on our cone there. Radius of r, height of h, angle at the top we'll call theta. Okay, I'm going to draw all the forces that are acting on Bob. Or maybe you can tell me some of the forces that are acting on Bob.
Gravity.
The force due to gravity, correct.
Yes.
That would be weight.
That's fine,
Yeah. Anyone else care to offer up a suggestion? Tension, it's connected to a string. And we said whenever it has a string, there'll be tension going up there. So there we go. Tension up the string, always away from Bob. Doesn't like Bob tension. And there's force due to gravity going down. That's it. Remember, centripetal force is a resultant force. It's not an actual force that's on there. Okay, so theta, well, we know that's the angle as angular velocity. Now, just like we did with projectile motion, it's a lot easier to break this up into straight line motion. So we'll look at horizontal and vertical. So the resultant forces. Now, mx double dot, or is mv squared on r, or mr omega squared. Remember, that becomes horizontally our resultant force, because horizontally all Bob's doing is moving in a circle. So horizontally it's just circular motion. Okay. Whereas vertically, well, unless I placed a force on it by making it spin faster or slower, it stayed at the same horizontal level. So unless an extra force was imparted upon it, as Newton's laws said, it will remain there. So there was no, the resultant force vertically was zero, because it was just staying in that horizontal circle. Okay, so my horizontal forces, I know, are all going to sum up to be mv squared on r, or mr omega squared if you're using angular velocity. Vertically, they're all going to sum to be zero. Okay. Let's resolve the tension, because whilst gravity, that's fine, I know that's purely vertical, there's going to be a component of tension horizontally and a component vertically. So to get to that same point of the green arrow, I could go left and then up, or if you prefer, I could go up and then left, but either way, you're still doing the same two things. So there's Bob, but just horizontally, all we have is to the left. And we can do a bit of trig there. We know that would be t sine theta. T sine theta. Easy way I look at it is go, oh, well, t is the hypotenuse. It's the opposite side, so I know it's sine. It'll end up being sine theta. And that's it. So t sine theta is mv squared on r. Now, vertically, I'd have t cos theta going up, and I've got mg going down. So they will add together, but of course mg is negative, it's in the opposite direction to t cos theta, is equal to 0. It doesn't actually matter with this vertical, because they sum to be 0, it doesn't matter whether you make up being positive or down being positive, because they sum to be 0. I've made up being positive, so that's why t cos theta was positive. I could have just as easily have made down being positive, and then I would have had mg minus t cos theta equals 0. Still get the same equation, t cos theta equals mg. It sort of made more sense to make up positive, because that's what we're used to. Okay, I'm going to play around with that, because I don't know what the tension is, but I can eliminate the tension. Because if I say, well, t sine theta over t cos theta, the t's will cancel. That'll be mv squared on r times 1 on mg. So I get tan theta is v squared on rg. Okay? Or if I was using angular velocity, I would have ended up with r omega squared on g. But if you have a look at our triangle, the dimensions that we drew, the cone, if you like, tan theta is the radius over the height. So I could substitute that in. V squared on rg is the radius over the height. I can rearrange this to find whatever it is I'm looking for. So if it was the height of the pendulum, I could rearrange this and say, oh, okay, I know the height is r squared g on v squared. Here's where it looks really nicer and a lot simpler. If it's angular velocity, it's g on omega squared. So it's inversely proportional to the angular velocity squared. So the greater the angular velocity, the smaller h is. That's why my helicopter rose. I sped it up, it went up. So there's some implications there. The depth of the pendulum, that's what h was, so the depth, how far down, it's independent of the length of the string. It's nowhere in there. When I look at this one, that makes it more obvious, g on omega squared. It's got nothing to do with the length of the string. Other than, of course, it can't be further down than the length of the string because that would be a physical impossibility. But other than that, it's totally independent of the length of the string. As the speed increases, we saw that Bob rose. Let's do an example. So, good old Bob. We start off going 60 revolutions per minute. And then I'm going to speed it up to 90 revolutions per minute. And we're going to find how far up does my helicopter, Bob, rise. There's Bob. So I would start this question by going, okay, what are my forces? There's tension. There's mg. And there's some dimensions of the cone. They'll come in handy. All right. I know horizontally, it's only circular motion. So it's mv squared on r. Vertical forces are going to be 0. Basically, I'm just doing exactly the same as what I just did. So, component of tension, T sine theta, is horizontal. T sine theta is, well, it makes more sense to use the angular velocity in this one because they're talking about revolutions per minute. So, mr omega squared. Vertically, T cos theta, mg. And so we get T cos theta is mg. And so I get tan theta is r omega squared on g, but looking at the dimensions of my cone, I know tan theta is r on h. So r omega squared on g is r on h. There's our h is g on omega squared. Well, we want to know how it changed. Started off 60 revolutions per minute, which is 120 pi on 60 radians, 2 pi radians per second. So the height is g on 4 pi squared when I sub that in. We then sped it up to 90 revolutions per minute. Oh, conveniently, that works out to 3 pi radians per second. Sub that in, I get g on 9 pi squared. So how far did it rise? Must be the difference between the two. And rounding that off, it's about 0.14 of a metre would rise. Okay, let's have a look at an HSC1 of 2002. There's our particle of mass m suspended in the string, but the other interesting thing is it not only is it moving as a conical pendulum, at this point it's sitting on a cone. So it's on a cone and doing a conical pendulum. Now we've been told some dimensions here. The angle of the cone at the vertex is 2 alpha. So alpha on either side of the vertical they've put there. Alpha they've told us is bigger than pi on 4, 45 degrees. The string coincidentally makes an angle of alpha with the horizontal up there. And they've told us about all the forces that are acting on the particle. String, tension. Force due to gravity, mg. And there's this other thing, n. Go right back to when I first started talking about Newton's laws. And remember me standing here, but not going crushing through the floor. Whenever you're making contact with a surface, there is a reaction force, sometimes called a normal force, to you, to the surface. So it balances that out. So whenever the particle makes contact, there will be a normal force. They've called it N for normal. As I say, sometimes just R for reaction, because you'll see they've called it normal reaction. Normal force, it will be at right angles to the surface. So there's the right angle there. So that's another force that's in play in this problem. Show, with the aid of a diagram, that the vertical component of the normal force is n sine alpha. Okay, it's good old Bob. Let's put all the forces in. There was tension going up the string. There's my two components I'm going to need for tension. So I'll just draw that in. I can work out through a bit of geometry on that problem, alpha ends up being down there. Okay, there is a normal force which is at right angles to the cone. Now, where is alpha in this problem? Just over here, I'm going to redraw. Whoop, there we go. Remember, it's sitting on a cone. The cone, they said the angle was 2 alpha, alpha either side of the vertical. So if we use some geometry here, we can work out where in our force diagram does alpha go. Well, I can put alpha there, alternate angles. We said the normal force was at right angles, so therefore alpha goes up there, because the one here would be 90 minus alpha. It's a right angle triangle, so alpha must be at the top in this diagram. So okay, I now know the position of alpha. Gravity was purely vertical. That made life a little bit easier. Okay. We want to find the vertical component. I've just called it C for component. C over n is sine alpha, C is n sine alpha. So there we go. I've proved that the vertical component is n sine alpha with the aid of a diagram. Part B, a bit more fun. We're going to show that T plus n is mg on sine alpha. And then we're going to find an expression for T minus n, and we want it all in terms of the mass, the length of the string, and the angular velocity. Okay, horizontally, what's happening? Just circular motion. So horizontally, I'm using mr omega squared because I notice here it says in terms of omega. So it makes sense to use mr omega squared for this one. There's Bob. We will have horizontal component of tension, that'll be T cos alpha, and horizontal for the normal force will be N cos alpha. They're in opposite directions. How do I know which way is positive? Why did I make it T cos alpha minus N cos alpha and not N cos alpha minus T cos alpha? Why?
Because our resultant force, like if we let it be positive, is towards the center.
Right. The resultant force, we're talking circular motion. We said the resultant force was the centripetal force. And we said centripetal force is always to the center of the circle. So if you imagine our particle going around the cone, then in the position that it's in the diagram, it would be to the left, going towards the center of the circle. So that's why T cos alpha is positive. N cos alpha will be negative. Okay. Vertical forces are equal to 0. So again, we're just running around on this cone. We're not moving up or down. Let's have a look at all those forces. We have T sine alpha going up, N sine alpha going up. We also have mg going down. In this case, it doesn't matter which one I make positive. So traditionally, we tend to go up. So T sine alpha plus N sine alpha minus mg is 0. I get T sine alpha plus N sine alpha is mg. Okay. First part of the problem was to find an expression. Well, they told us what it has to be, but hopefully you can see where it's going to come from. We've got to get T plus N. So T sine alpha plus N sine alpha is mg. So T plus N sine alpha is mg, T plus N, mg and sine alpha. They then said find a similar one for T minus N. Well, over on our horizontal forces, we said T cos alpha minus N cos alpha was mr omega squared. So I get T minus N is mr omega squared on cos alpha. Not quite there, because they said they want it in terms of L omega. What else was there? What was the third variable? M? Okay. Well, we got the M. We got the omega. But the other thing we've got there is na and a cos alpha and not the length of the string. All right. If we go back to our picture, we can see that, hang on, R on L is cos alpha. So the radius of the circle over the length of the string is the cosine of alpha. So T minus N ends up being ml omega squared. ml omega squared. Now, the angular velocity is increased until n equals 0. Now, n equals 0 is when it loses contact. Because whilst it's in contact with the surface, there must be a reaction or a normal force. So it must have a value. As soon as it loses contact, it no longer has a value because it no longer has that reaction force. So at the point when it loses contact, that's when n equals 0. So we're going to find an expression for the value of omega going to be in terms of alpha, length of the string, and g. So when n equals 0, T is mg on sine alpha. That's for my first expression. But I also know T will be ml omega squared. Well, it's the same tension. I can't change that. So therefore, I can eliminate the T. Mg on sine alpha is ml omega squared. Let's make omega the subject. And there is our answer. The square root of g on L sine alpha. Wow. Well, that was funny.